All right. Well, happy Monday, and it's week 8, and um, time is ticking right along. Okay, so I just want to kind of give you a quick rundown of what we've got coming up. So, at the risk of I don't want to discourage attendance, but um, basically, um, I'm not going to have a lecture review quiz today. On Wednesday, you have your exam, and then uh, Friday will be a pre-recorded lecture. Ninth week, I only plan on teaching on Monday, and that will also be a pre-recorded lecture. Okay, and then 10th week and finals week, we're just gonna have final presentations. We're not gonna be meeting in class. Okay, so um, maybe I will maybe I'll write all of this down. Okay, I'll send a announcement. Okay, so plans for the rest of the quarter, and sign up for a final presentations time slot. Okay, so week 8 Wednesday will be exam. Week 8 Friday, pre-recorded lecture, no view quiz. Week 9 Monday, also pre-recorded lecture. These lectures are just going to cover topics that I think could be useful for some groups in their analysis, but not necessarily for all groups, if that makes sense, okay? Because everybody's group's project data is a little bit different. So like today's lecture, we're going to be looking at correlation and linear regression, and that will definitely be useful, actually probably to most groups, okay? But certainly some groups more than others, okay? And we're just going to cover a little bit of surface stuff. Same kind of thing for Friday's lecture and then Monday's lecture. And then week 9 Wednesday, no class. Happy Thanksgiving. And then also, I guess week 9 Wednesday and Friday. Okay, so no class on Wednesday and Friday of next week, and then week 10 will be final presentations. And then week 11, I guess finals week, will also be final presentations. All right, I will, some extra credit will be offered for groups presenting during week 10. Oh, okay, wait. All right, so week 10, final presentations. I will have one class, we will have one session, week 10 Friday, okay? Will be optional in-class presentations for groups that volunteer. And I'll talk about this. These are 5 minutes each, and extra credit, and there will be a sign-up sheet. So I'll send out another announcement with basically sign-ups. But I'll have time slots for your groups to present during week 10 and week 11, and to kind of encourage you guys to do it during week 10. I will offer a little bit of extra credit. All right, and then on week 10 Friday, so the very kind of last day of class, we'll have in-class presentations. Okay, about 5 minutes each. We can squeeze in about probably like 8 or 9 groups. Okay, so I think there's 13 groups, so not everyone's going to present, but also in the past, not all 13 groups wanted to present. So But I think it's kind of fun to just see like what other groups have done, because usually the projects come out. I'm always impressed by the different projects that different groups produce, and anyway, so these last few weeks, not going to be covering a whole lot of new stuff. Like today's material, not going to show up on the exam. I'm not going to have view quizzes. It's going to be kind of like, if this is helpful for your group, take a look at it. What I really want you guys to be doing is working on your final projects, and I really think when you're working on the final project and you're working with a little bit of a messy data set, right? Like a data set that's not just tailor-made for your homework or something, but it's like coming from real life. You encounter some issues, and I think that's where you really learn and start to understand like the different aspects of data analysis. Of course, everybody's data is different, so the kind of exposure and things you're doing will be a little bit different from group to group, but I do think there's still a lot of kind of beneficial learning happening in each of these things. That the hard part is with a group project, it is possible for a couple individuals to do less work than others, and that's going to be the case really like for the rest of your life in terms of like working with colleagues and stuff. But hopefully you can kind of keep one another accountable and encourage each other to put forth your best efforts. I have office hours, lots of office hours, and if you have any questions as far as like, is our group approaching this data the right way? Like, this is what we're seeing so far. What do you think we should be doing next? We have this idea and we're not quite sure what code we need to write to get this to happen. I'm happy to help you with all of that, okay? I want the project to be a positive experience for you. I want the project to be something where you feel proud of what you've produced and feel like you've learned something along the way. And I don't want it to feel like it's a huge mystery. You have no idea what you're supposed to be doing. I've met with all of your groups, all of you guys, for your different project proposals, and hopefully, and some of them I had concerns, but hopefully those concerns are helpful to kind of guide and direct you into a good analysis there. Okay. Anyway, I will. So this is kind of the plan for the rest of the quarter. I will create a sign-up sheet. And please sign up for a final presentation time slot. Okay, that's for the rest of the quarter. All right, so we'll so that's that. Okay. Regarding the exam on Wednesday, I'm going to email out a seating chart. I know that's weird, but it has helped in terms of just relaxing suspicions, right? So so I'll send out a seating chart, and yeah, question?
Regarding the in-class presentation.
Yes.
Should everyone in our group come? Is it okay for one or two?
I would much prefer if I feel like if the person doesn't come, they shouldn't get the extra credit for that, if that makes sense. So we'll say if you want the extra credit, you got to be here for the presentation. Okay. Yeah. Okay. And then as you guys are meeting, I know it's a little bit annoying to kind of document your meetings and stuff. take meeting notes. But I do, it is kind of helpful for me, especially at the end, to just kind of review, and it's the least bit we can do to kind of try to keep people accountable, because in the meeting notes you write down like what each of the team members contributed. So that's to have a paper record of what you guys are doing. Okay. Any questions before I dive into today's topic? Okay. All right. So we're not. So basically, I won't see you at all next week. Okay, because it'll be a pre-recorded lecture, and then it's Thanksgiving. I always cancel the Wednesday class anyway, and then week 10, it'll be final presentation. So I'll just see you guys on Friday of week 10 for the extra credit presentations and things like that. Okay. All right. Okay. Well, today I want to talk a little bit about correlation and simple linear regression. This could be a helpful topic for different groups. Okay. And so, and the idea behind correlation and linear regression is that we are looking to see if we can quantify a relationship between numeric variables. Okay, so this only works for numeric variables. It does not work for categorical variables. And you have to be careful. Some categorical variables look like numbers, like zip code, area code, or if in your data a category is coded as category 1, category 2, category 3, those look like numbers, but they are categorical variables, and do not try to use linear regression for categorical variables. One indication that you might have categorical variables and you treated it like a and you're doing linear regression and something, is like when you plot it, and if you see either vertical lines of dots or horizontal lines of dots, okay, that's an indication that your variable is discrete. Okay, and discrete isn't necessarily categorical, okay, but it is something you have to be aware of. So like in your first homework assignment, you plotted like hurricane wind speeds, right? And then there was like horizontal lines of dots. Okay? And that's because hurricane wind speed was measured to the nearest 5 miles per hour. And that's fine. It's still a numeric measure. We can still treat it like a numeric thing. Okay. But if you have something like category 1, category 2, category 3, it might get printed as horizontal dots or vertical dots, vertical lines of dots and things like that. Okay, but anyway, the example here is, let's say you're looking at housing data for a certain neighborhood, and we're looking at the size of the house measured in square feet and its estimated value. And in general, we see this trend that bigger houses, okay, if the house has more square feet, it has a higher value. Smaller houses, less square feet, will have a lower value. And we'd say, yeah, there's a relationship between the size and the price of a house, okay? And correlation linear regression, this allows us to quantify the relationship, okay? Rather than just having a very kind of generic statement of like the bigger house means a higher cost, we can say if a house has 1 additional square foot of size, it's associated with an increase of $350 to the value of the house, something like that, right? We can be very kind of specific. This is an example of data taken from the Census Bureau, and the Census Bureau has kept track of all kinds of different information, demographic information. One of the things they look at is age of first marriage. Okay, so for example, in the year 2019, people got married. Okay, and they collect some information, and so some people it's their first marriage. Some people, it's not their first marriage, second marriage, third marriage, whatever, right? And basically, they just took all of the data where it said they asked, men, self-identified men, is this your first marriage? If so, how old are you? Okay, and then they asked women, is this your first marriage? If so, how old are you? Right? And it's not necessarily that two people got married to each other or something, okay? Because you could have, marriages where for one, it's their first marriage, and for the other person, it's not their first marriage, okay? That doesn't matter. It's just, oh, is it your first marriage? Yes? Okay, how old are you? Right? So that's how it goes. And then, and they said, okay, in the year 2019, all the people who had first marriages that were men, on average, the average age was 29.8. Okay, when we asked people who was their first marriage and it was a woman, on average, the average age was 28. Right, so some people are older, some people are younger. This is what we have, and they kind of kept track of this, like every year. I think prior to 1940, it was every decade, but we can kind of plot this. And if you plot this, this is what the data looks like, okay? So on the x-axis, I have men's average age of first marriage, and on the y-axis, we have women's average age of first marriage. And so each dot is a different kind of moment in history, right? Where this dot represents 2019, right? And I don't know what the other dots are, but this dot here is a moment in history where the average age of first marriage for men was like maybe 25 and a half, and the average age of first marriage for women was like 23.4 or something like that, okay? And there were other moments in history where the average age of first marriage for men was like 23, and the average age of first marriage for women was 20 and a half or something like that, right? So these are just kind of different, and again, these aren't all labeled, so but this is all that we're seeing, right? And but we see a very kind of strong relationship, right? And up here, these in the top right-hand corner, these are times, moments in history where the average age of first marriage for men is between 28 and 30 years, and for women who got married for the first time that year, average age was somewhere between 26 and 28. This is kind of what we have there, right? And then here we have a bunch of years. There's actually quite a few dots where there were periods of time where the average age of first marriage for men was around 23, between 22 and 23 years. And for women, it was between 20 and 21 years, right? Which is like, some of you might be that age right now. And it feels, it feels awkward thinking about that, right? But there were times in history like that. And so what we see is there's kind of like, overall, in general, in years where men got married at a young age, those also corresponded to years where women tended to get married at a younger age. In years where men tended to get married at a higher age, those correspond to years where women also got married at a higher age. There's a couple, most of the time they're right along this axis. There's a couple of years right here, like most of them, like there's kind of a 2-year-ish difference. Like the average age was around 26 and the average age for women is around 24. And here it's like 28 and 26. And here there's like there's a couple dots where there's like a 4-year difference, where average age of first marriage for men was 26 and the average age of first marriage for women was like 22 and something like that. Those are a couple moments in history there, but this is what we have. And so anyway, that is, can we kind of quantify this, from this kind of scatter plot, right? All right, so anyway, this is just whatever I had to say there. All right, here is another plot, and in this plot, I have I used facet grid, okay, and I have a plot for men and a separate plot for women, and on the x-axis we have different years, okay, and so here I'm not plotting average age of first marriage for men and women, but I'm plotting average age of first marriage for men against the year. So this is around 1900 and 1890. Okay, so in 1890, average age of first marriage for men was around 26. And then in 1900, it was still around 26. 1910, it was around 25. And actually, as kind of, here it is in 1920, 1930, 1940, 1950, and then we started taking data every single year. Average age of first marriage was started off around 26 and then declined until it hit its lowest point around 1960, where the average age of first marriage for men was around 22 and a half. 22 and a half. Okay. And then after 1960, it seems like almost every single year, the average age of first marriage kind of increased a little bit. So in 1960, it was around 22 and a half. By around 1980, it was around 25. By around the year 2000, average age of first marriage was around 26 and a half, 27. And then by the year 2019, it's at 29.8, right? So we see this kind of down and then up. And then interestingly enough, for women, it looks very similar, but just kind of shifted down a couple years. All right. So average age of first marriage for women starts off around 22, goes down, maybe around 21 here, and then drops 1960, reaches kind of the bottom, 1959, 1958, 1960, something around there, around 20. And then every year after that, kind of a steady increase. So by 1980, it's back up to around 22 and a half. By the year 2000, average age is around 25. And by the year 2019, it's about 28. Okay, so that's what we see here. So as far as, so both of these scatter plots, this one and this one, I think are both useful. But as far as linear regression goes, we can only do it for this, okay? Because linear regression says, like, can we take a straight line and fit it through the thing? And so we can do that for here. Over here, we can't. We can't just use a single straight line. Okay. If I cut off the data at like 1960, then maybe if I just start my data here, I can see there's a linear trend after 1960. Okay. After 1960, we can say it's close to a linear trend. It's not perfect, but pretty close. But if we want to take the whole data into account, linear regression and correlation do not work, okay? So this is kind of the key, is that they can't be defined with a single straight line, right? There is a very strong relationship. We can describe it, but trying to describe it with a single straight line, it's not going to work. So as far as correlation and linear regression goes, it only works for single straight lines, okay? At least what we're covering in kind of at this level. There's certainly regression tools and things that we can use for more complicated relationships, but we got to start off with just this straight line version. Yes?
Just for this example, is there any way you could plot two linear regressions in the same plot?
Yeah. So you can split the data, right? So in this case, yeah, it would make sense. I would say, yeah, let's split the data around 1960, okay? And then after 1960, we do a linear regression, and then prior to 1960, we do a separate one.
Okay? And you could do those two in the same graph.
Yes, you would have to. It would require a bit of stitching. Okay, so you'd have to first separate the data. You'd have to split the data here, and then there's a tool to do linear regression. And then once you have that, then you separate the data and you do the tool for linear regression over here. And then yes, you can
join them back.
You can join them back together into the same plot. But you might get like unless you put an extra, there's a way, but like the default is it's going to draw a straight line and it's going to keep going this way, and then you'll have the line next. And there are ways you can just say like, no, we want to stop it at 1960 and we want to start at 1960. You can do that. It's
Yeah, because I know
it's a little tedious, but it can be done.
just comparing the different stuff. I've done it in Excel and then just make a linear regression with things to Excel.
Yeah.
Couldn't do that enough.
It can be done. It can be done. It's just everything requires a little bit of like a little extra, like start here and here. Yeah, that's all. Okay, so overall, we're going to just start with kind of this idea of like describing relationships. And again, kind of the key is, as far as this goes, for linear, we just want to do linear. Linear just means straight line relationship. And then if there's curvature, or if there's a bend, or if it changes direction, we're going to just say it's nonlinear. Okay, and again, if you are a stats and data science major or data theory or something, you will take probably Stats 101A, and 101A is all on regression, and you will start off with linear regression, and then you'll get more advanced and be able to address nonlinear relationships. Okay, but we'll just start off with kind of the linear thing, and the way you decide if something looks linear or not is you create a scatter plot and you look at it. Okay, and it feels very kind of unscientific. And there are tests that exist to decide if something is linear or not. But honestly, our eyes and our brains are very, very, very well equipped for pattern recognition and seeing linear relationships. Okay, like our brains want to identify patterns. Our brains want to connect the dots. Okay, there's just kind of a thing there, and so when we see this, our brains automatically just go, oh yeah, that looks kind of linear, right? And this is why we look up at the stars and we see shapes and clouds, and you're driving along the highway past farms and you see like, oh, all of these things kind of line up and stuff. So your eyes and your brain do a really good job at identifying whether something looks linear. And then, if you're kind of like, well, I'm not quite sure if it's linear or not, like that's the answer. It's probably not quite sure if it's linear or not. Okay. So yeah, just create a scatter plot, look at it, geom_point, look at that and say, hey, does that look kind of linear? And then make a judgment call. Okay. And what you'll find is that if you subset your data, you might find linear relationships, but if you look at the whole entire thing, it might not look linear. These are the kinds of things I want you to explore with curiosity and see if you can identify these things. Okay. When you look at the relationship, overall, we can say the direction of the relationship is positive, negative, or neither. Okay. Positive means large values of x go with large values of y, and small values of x go with small values of y. Basically, they go up and down together. And negative means they move in opposite directions. You have large x, that goes with small y. Small x goes with large y. Okay, and then neither means neither of these trends hold. So, positive trend, okay, overall, positive trend is something like the age of a car and how many miles have been driven on the car. Okay, in general, older cars, so that means large X value for the age, tend to have more mileage driven on it, large value for Y. Okay, small value for X, so a newer car will in general have fewer miles driven on it, smaller Y. So that's going to be positive. Okay, of course there's going to be some exceptions, but that's generally what we have. Okay, and so a lot of kind of things that are related to size and growth and things like that, those will generally be positively related. So like height and arm span, general positive relationship. Taller people have longer arms, shorter people have shorter arms in general. Okay, stuff like that. And things like, especially for like sports things, teams with, more points tend to also have more other kind of positive things. So like basketball, like, better teams will have more points and more rebounds and things like that. Generally, these things will be kind of positively correlated. Okay. Football, more points scored will also correspond to kind of probably total more yards rushing, more yards passing altogether, things like that. Okay. We have negative trends. Negative, again, means large X goes with small y, small x goes with large y. So this is an interesting data set. We were looking at different nations, and we have literacy rate and total births per woman, and this is what is actually explaining the relationship here. That is beyond the scope of our class, but can we identify that this relationship does exist? When we plot it, we see there's a negative relationship. So in countries where there tended to be higher literacy rates, okay, tend to correspond to fewer total births per woman. And then in countries where there's low literacy rates, okay, those tend correspond to countries where there's higher births per woman, okay? But again, we have to be very careful not to draw cause and effect conclusions, and I will I will kind of be a little bit harsh and take off points and stuff if I feel like you guys are overstepping the kinds of conclusions you're allowed to be making with your thing, right? Just hearing a lot of your kind of project proposals, there's a desire. We want to be able to draw these kind of cause and effect conclusions, all right? A lot of your research questions in your proposals were like, which factors have the biggest impact on this outcome, right? And that's like a natural thing that we want to ask. But factors having an impact implies there's this thing causes the other thing, okay? And we don't want to say that, right? We can say there's which variables seem to have highest associations, strongest relationships, things like that. But drawing a cause and effect thing, we have to be very careful, right? You would want to have some kind of external source other than just the data, okay? Some external source that you can cite that says this is indeed the thing that's going on, right? It would be a tragic misunderstanding of the data if somebody saw this, right? Governments saw this and said, oh, we're having we need to decrease literacy in order to increase the total number of births per woman, right? Like, a lot of nations, their populations are shrinking, right? That's like just, I don't know. There's lots of complicated reasons for, why people aren't having as many children as they were in years past, okay? And we don't want to say like, oh, the explanation is literacy. Take away the literacy. That would be. I mean, we can imagine some governments wanting to do something like that, but no, that is not the answer. Okay, so to draw some kind of thing like this, right? There's that we don't want to draw any kind of cause and effect relationship there. Okay. All right, here's an example of something where you have neither a positive nor a negative relationship. This one was they took times from a marathon race and they looked at how old was the participant and then how long did they take to complete. This was like some small non-competitive, marathon or something. And so at least in this data set, not a huge, real relationship. Okay, so you have people who were old that participated, and they, some finished quickly and some took a long time. People who participated that were young, and some took, finished quickly and some took a long time. People kind of in the middle, and some took quickly and some took a long time. So there's no real strong relationship here as far as like, do older people finish faster or do older people take longer as far as the marathon goes? We don't really have a relationship that we can establish there. Is that already? Oh my gosh. Okay. Been talking too slow. Here's another one, neither positive nor negative. On the low x has high values of y, but high x also has high values of y, and it's kind of like values in the middle of x that have small values of y. There's clearly a relationship, right? Like if I said draw a line, you would draw like a U-shaped thing. There's clearly a relationship, okay? And if I said, hey, try to make a prediction if x was 5, you would predict something around here. Trying to make a prediction if x is -5, you would be able to make a prediction. But is it linear? It's not linear, and it's not positive nor negative, okay? Yeah, question?
Yes.
This one?
Yeah, so I had a question about whether or not you can fit a linear relationship based on the domain of the values you're looking at.
Yeah, so if you wanted to, you could say, all right, let's draw some arbitrary cutoff like right here. And so for x greater, so x greater than 0, there's an overall positive relationship, but it's definitely not linear, okay? But maybe you might be able to argue x greater than 5 is close enough to linear that we could do a linear relationship and feel okay.
The overall graph looks like a quadratic graph, but if
Yeah,
you just look at
definitely.
like between like 3 or 5 or something, it could look.
Yeah. That's like one of the basic ideas of calculus is that like, you have these first order approximations when it's within a small thing, it's good enough. And yeah, so if you have a small enough range, yes, you can approximate, at a theoretical level, any function with a linear thing with a small enough x range. And the question comes down to, is it appropriate to use that for your particular data set? And in some cases, sure. It's like, the overall relationship may not be linear, but, we have data from January 2025 and March, April, and May of 2025, and so on and so forth. But something went wrong, and we didn't calculate it for February and March. Can we use linear regression to try to fill in those gaps? If January through, if like looking at December and January, and then March, April, May overall looks kind of linear, probably it's okay, right? If you're looking at that and it doesn't look linear, then we would say no. But so yeah, if within the window you're looking at looks kind of linear and you want to approximate it, the answer is a lot of times yes, it's okay. But then the answer is always it depends on your data, it depends on the situation, it depends on whether it makes sense or not. And I think this is why, like, is AI going to take all of our jobs? I don't know, right? At this point, my job can be replaced with a video recording of me. So, some students are using that anyway. But I do think there is, like, right now, we have, like, a deeper understanding of, like, oh, yeah, in this context, it makes sense and things like that. We have a little bit more awareness of some of the context and things like that, The AI does seem to be getting stronger and better every couple months. So I don't know. Maybe I will change my my tune. Okay. We've talked about direction. All right. Let's talk about the strength. Okay. And then strength is like, is the relationship weak or strong? And basically, it comes down to like when you create a scatter plot, is there lots of scatter or less scatter? All right. And so here, this is like the y-axis is someone's weight, and we're trying to predict someone's weight, and both of these things are positively related, positive relationships. Okay, height is positively related to weight. In general, taller people weigh more. In general, shorter people weigh less. Okay, but then also waist measurement is also positive related. Okay, in general, people with bigger waists weigh more. People with smaller waists weigh less. Okay, in general. And so what we find is that there's a stronger relationship. Okay, that if you wanted to predict someone's weight, it's more helpful to know their waist size than to know their height, because what we're seeing is less scatter here and more scatter over here. Okay. All right. And so, yeah, looking at this, age of first marriage for men and age of first marriage for women, positive relationship, I would say a very strong relationship. There's not a ton of scatter. Like if you knew the moment in time was when age of first marriage for men was 28, you could probably predict age of first marriage for women, quite accurately there. Okay. So anyway, that's what we have, and we are like running out of time. All right, I guess maybe I'll just continue this on Friday. So we have a statistic called the correlation, okay? And the correlation is done in R using COR, C-O-R, and you give it basically a vector of two numeric values, and it's always going to produce a value between positive 1 and negative 1. The sign of R is the direction, so positive values of R is positive relationship, negative values of R is a negative relationship. Values close to 0 mean a weak relationship, weak linear relationship, and values close to positive 1 or close to negative 1 would be a strong linear relationship, okay? But this only works if the relationship is already linear, okay? You can punch in, it's just the formula, so you can put in values and it will produce an R, but the R by itself doesn't tell you if the relationship is linear or not, okay? R by itself will not tell you if it's linear or not. You've got to plot it, you got to look at it, okay? So just examples, this is R is 0.72, here's more scatter, so R is closer to 0, R is 0.48. And here's like a ton of scatter, it's like barely positive, R is 0.19, okay? As R gets higher, you get less scatter. As R is closer to 0, you have more and more scatter, okay? And so the correlation is you just type in COR, and then you can either use $sign to pull out the column, or with Tidyverse, you do like marriage, select men, and then pull, and then you store it somewhere, and then you get your vector of X and you get your vector of Y values, okay? And then here's a couple kind of things. So the interpretation of R, this is probably the most important one, is only useful for a linear relationship. So technically you can calculate correlation for nonlinear relationships, but it's not going to be meaningful, okay? A correlation of 0 doesn't mean there's no association, just means that there's not a linear association. So like if I go back to this slide, okay, this is the wrong number, but this slide, if you calculate the correlation would be 0, but there's clearly a relationship. It's a U, it's like a parabola quadratic relationship. But if you calculate what's the correlation, it's going to come back and say it's 0. So not there, okay? And then the other thing is slope is unrelated to correlation. So if you change units, if you go from like, if you measure something in seconds and then you change it to hours, it's not going to affect correlation. It'll affect the slope, okay? If you go from feet to inches to centimeters or whatever, not going to affect the correlation. It will affect the slope, but not affect the correlation. Okay, we'll cover the linear regression stuff later. I guess we'll come back to it on Friday. But for now, as far as talking about correlation and creating scatter plots, that's a good place to start. And we'll stop here. Okay, we'll see you guys on Wednesday for the exam. I will email out a seating chart, so keep an eye out for that. And good luck as you guys study, and we'll see you then.